Okay, so hello everyone. Welcome to the ChartSpark course series of Fundamentals of Integrated Sensing and Communications. And today is lecture 3.1 with the title Communication-Centric ISAC Signal Processing. And our guest speaker today is Professor Fan Liu from Southeast University. And before we start, let me briefly introduce Professor Liu. Professor Fan Liu is currently a professor with the National Mobile Communications Research Laboratory, School of Information Science and Engineering, Southeast University, China. His research interests lie in the general area of signal processing and wireless communications, and in particular in the area of integrated sensing and communications. He has received many awards including the 2025 IEEE ComSoc and Information Society Joint Paper Award, the 2024 IEEE SPS Best Paper Award, 2024 IEEE SPS Download G-Think Overview Paper Award, 2024 IEEE ComSoc Asian Pacific Outstanding Paper Award, 2023 IEEE ComSoc Stephen O'Rice Prize, and 2021 IEEE SPS Young Author Best Paper Award. So Professor Liu is a very well-established scholar. Now, let's welcome Professor Liu to give us his talk. Welcome.
Okay, many thanks, Dr. Sun, for your very nice introduction. So let me first share my screen. Okay, can you see my screen now?
Yes.
Okay, great. So hello everyone. Again, I'm going to present I think this is the fourth lecture of this course series on fundamentals of ISAC. So today my presentation will be focused on communication-centric ISAC signal processing. So in the previous three lectures, we have already delivered the lectures on introduction on ISAC and information theory on ISAC. So today, let's look at some particular signal processing technique for ISAC. Okay, so I'm not going to introduce the background of ISAC. We have already, there are lots of introduction on this in the previous lectures. So I'm going to start from this ISAC waveform design methodologies. So basically, there are three types of ISAC waveform design philosophies. One is sensing-centric, which means that we could embed information in the legacy radar waveforms like chirp or like binary phase-coded waveform or polyphase-coded waveform. So basically, it has negligible impact on the sensing performance, but it may result in low spectral efficiency and incompatibility with current cellular networks. So that is because the current cellular networks will never be using, like chirp waveforms for communication. So that is a huge issue for sensing-centric design. And the second category, which is our today's focus, is communication-centric design, which means that we can, perform sensing with standardized communication waveforms, like OFDM, single carrier, even like OTFS, AFDM. So this kind of design have negligible impact on communication performance and is fully compatible with the cellular networks. But the sensing performance may be seriously degraded due to the random data payload signals. So I will, elaborate more on this part. And finally, we have joint design. So we will introduce joint design in our next lecture. So joint design is to conceive novel waveform based on nonlinear optimization techniques. So basically, it can very flexibly achieve a scalable sensing communication trade-off but it can be very challenging to implement in practical systems. Okay, so today we're going to look at the communication-centric design. Okay, so communication-centric ISAC means that we should use standardized, default waveform, communication waveform to do sensing. For example, if we look at the current 5G NR-based ISAC, 5G NR-based scheme, mostly used in 5G Advanced. So they basically exploit physical layer reference signals for sensing, like CSI-RS, DMRS, PTRS. So these are RS means reference signal. So these are different reference signals, also known as payloads, and they can be used for different purposes. Okay, and there are also some naive approach, like just use like 10% of the time resources to transmit chirp signals for sensing, and they use the remaining 90% for standard communication. But this kind of design, which can be very easily, like I just mentioned, which can be very easily implemented, but may have very poor performance, either both in sensing and communication. Okay, so that is because reference signals, so they occupy only 10 to 15% of the time frequency resources in the NR protocols or in the frame structures. Okay, so the majority of the resources is allocated to the data payload, so they occupy more than 85% of the resources. And if we're going to improve our sensing performance, we'll have to fully exploit these data payload signals, so such that we can have much more bandwidth, much more time resources, and we can improve our range resolution and the Doppler resolution, and also the accuracy of sensing. Okay, so we need to reuse the data payload in addition to the reference signals for sensing. So that is the whole aim of the communication-centric ISAC. Now, if we're going to reuse data, communication data to do sensing, then we have to pay attention to this deterministic-random trade-off, which has already been introduced in our last lecture by Professor Yifeng Shun. So this was the paper by Professor Shun in 2023 on the fundamental trade-off in ISAC on the Gaussian channels. So for the first time, we revealed that there's this deterministic random trade-off between sensing and communication. So to elaborate, radar systems, they typically employ well-designed deterministic signals for target sensing, like chirp signals, like phase-coded sequences with very good ambiguity properties. But in order to convey information, communication data signals have to be random. For example, we know that in the Gaussian channel, Gaussian codebook achieves the capacity. And also in practical systems, we use QUAM and PSK constellations. Okay, so to convey information, communication data signals have to be random. They are typically randomly drawn from some given codebooks. And so from this paper, also from Professor Shun's last lecture, we know that sensing with random signals leads to performance degradation. Okay, so here, this is an example for Gaussian channels, that if we're going to achieve the Gaussian channel capacity, we have to transmit Gaussian distributed code words. But for sensing, basically we need to have its the modulus of the signals to be constant. Okay, so as you can see, compared to the Gaussian constellation, this constant modulus constellation will have less degrees of freedom and less randomness. Okay, but it achieves better sensing performance. So that is a so-called deterministic random trade-off. Okay, So we have to now, so that is the basic information theoretical insights that we have learned from previous works, but this is just a theoretical framework. So we have to look at what is the DRT, deterministic random trade-off, look like in a practical communication system. So before that, we have to answer very basic question: what is the general structure of a communication signal? So this is a very fundamental question, and I think most of us, we have learned something about this question in our textbooks like communication principles, wireless communications. But can we represent a general structure of a communication signal using a general mathematical formulation? So the answer is yes. So basically, in its simplest form, we could represent a communication signal by 3 blocks. Okay, just 3 blocks. So the input would be some random bit stream. So this kind of bit stream can be coded or uncoded like this. And from this bit stream, we have to first map these bit sequences to a constellation sequence like this. Okay, so we need a constellation mapping block here. So this is the first block. So once we have these constellation symbols, we have to convey these symbols on some modulation basis. So in this case, we need to precode these constellation symbols with a unitary precoder. This is a unitary matrix, which is also known as waveform. Okay, so we'll look at the some particular examples of this unitary matrix. And at this stage, we still have discrete samples, but in order to transmit over the air, we have to convert these discrete samples into continuous baseband signal. So we need a pulse shaping in this case. Okay. So as you can see, a pulse shaping is actually a filter that converts discrete time domain samples into the continuous time signals. So you can imagine that every this discrete X will be attached with a pulse. So this pulse we denote by PT. So as you can see, for the nth symbol, we could we need to attach a time shifted pulse by NT with this XN. So I'll show more details here. So NT here, T is the duration of the symbol. Okay, so as you can see in its simplest form, we have 3 blocks. So constellation symbols, orthonormal modulation basis, and the pulse shaping filter. So then a very basic question is that how do K components of a communication system like this affect the sensing performance? So this is a very, very fundamental question. And I believe no one has, rigorously, analyzed this before. Okay. So I think this is a very important, issue that we need to look at. Okay, now let's look at these blocks one by one. The first one is the constellation mapping, or the IID constellation symbols. Okay, so first of all, we assume that we consider a constellation that has this kind of property. It has 0 mean, unit variance, so its variance is equal to 1, and the 0 pseudo variance. So here you can compare with this pseudo variance with the standard variance. They are different, as you can see. Here we have an absolute value, and here we have no absolute value. And this is known as pseudo variance. And if it is equal to 0, that means the constellation has a certain, rotationally invariance. So for example, PSK, right? So if you rotate a PSK, you can have the same constellation. And the QAM signal, QAM constellation, for example, if you have a square QAM like 16 QAM, then if you rotate a 16 QAM by, let's say, 45 degree, by 90 degree, then you get the same, constellation. right? And also 64 QAM. If you rotate a 64 QAM by 90 degrees, you get a sim constellation. So that's all due to the fact that their pseudo variance is 0. Okay. Okay, and so this is a very generic, conditions for our constellation, and we can see that most of the PSK and quantum constellation they satisfy these constraints. And also, we need these symbols to be IID, so independently identically distributed. Okay. Another very important value of a constellation is the so-called kurtosis, which is defined like this. So under these three conditions, the kurtosis is actually equal to the fourth moment, right? So the fourth moment is, you can see that the expectation of the fourth power of S, okay, S is a constellation. So we can actually compute the kurtosis for some typical constellations. For example, every PSK constellation has a kurtosis of 1 because they have the same magnitude for every constellation point. And for 16 QAM, the kurtosis is 1.32, and 64 QAM is 1.381. So as you can see, all the QAM constellation they have, and also PSK constellation, they have a kurtosis value that is less than 2. Okay. So as you can, so it's very interesting to see that if S is Gaussian distributed, if it is zero mean unit variance Gaussian distributed, then its kurtosis is exactly 2. Okay, so with this Gaussian constellation as a benchmark, we could very naturally divide all the constellations into 2 categories. One is sub-Gaussian, which has kurtosis less than 2, and the other is super Gaussian, which has kurtosis larger than 2. So the examples of sub-Gaussian include the QAM and the PSK, as you can see here. And the examples for super Gaussian include like index modulation and some very specific form of APSK. So standard APSK, they are also sub-Gaussian, but if you have some APSK with drastically varying amplitudes, for example, if we consider 64 APSK, which has 4 circles, and each circle has a radius that is exponentially growing, then this APSK constellation has a kurtosis larger than 2, which is super Gaussian. Okay, so we have these 2 categories, super Gaussian and sub-Gaussian. Typically we are concerned about the sub-Gaussian constellations because QAM and PSK, they are the most frequently used constellations. Now, with this kind of constellation symbols, we have the first question. So how to achieve the trade-off between sensing and communication through the constellation design and in particular constellation shaping? So this is a very specific term that has been used in communication theory. Okay, so this is our first question. Okay, then our second question is about the modulation basis, which is this unitary matrix here. So as you can see, so if we record this figure, we have beta stream mapped to constellation symbols, and we have to modulate these symbols on some waveforms, on some modulation basis. Okay, then as you can see, this modulation basis can be modeled as a unitary matrix, this U matrix here. Okay, and this S contains the IID constellation symbols that we have introduced in the previous slide. Okay, so this U is a unitary matrix, and here are some typical examples. Single carrier. So before we introduce, we should note that this X is a time domain signal. Okay, this is a time domain sequence. So single carrier means that this unitary matrix is nothing but an identity matrix. Okay, so in this case, we're just transmit these constellation symbols consecutively over the time domain, so one by one. Okay, and then the other modulation basis, which is the current by default waveform in 4G and 5G, is OFDM, in which case this U is an IDFT matrix. Okay, so here Fn is the size n DFT matrix. So if you impose a Hermitian here, this is IDFT, which is again a unitary matrix. Okay, so if you use OFDM, that means you put these symbols over the frequency domain. Okay, and then the third example is a CDMA, and in particular CDMA 2000. Here, in this case, you can be a Hadamard matrix, Cn. So this is a Hadamard matrix of size n, okay, and which has been extensively used in 3G era. And then this is the recently emerging waveform called OTFS, so orthogonal time frequency space waveform. So it has a Kronecker structure, as you can see. We have size m IDFT matrix, Kronecker with size L identity matrix. And if you put this, unitary matrix on the S, then these symbols are placed in the so-called delay Doppler domain. Okay, so this is OTFS, and again, this is a unitary matrix because the Kronecker product of two unitary matrices is still unitary. Okay, so this is OTFS. And finally, we have AFDM. So here, AFDM means affine frequency division multiplexing, which has this kind of structure. Again, we have an IDFT matrix in the middle of two, diagonal matrices. So here, this diagonal matrices has this kind of structure. They has, just phase terms. They have constant modulus. But in this phase term, you can see that they have this square over these indices. Okay, so here we also have this C, parameter on the phases. So this is actually to use, multiple chirp waveforms as modulation basis to carry these symbols. Okay, and these two waveforms, so these are older waveforms, as we can see. These are classical ones, and these are new ones, right? So they are claimed that they can have achieve very better performance in very high mobility scenarios compared to OFDM. Okay, so here we have the second question: which modulation basis has the optimal sensing performance? So every unitary matrix is basically a modulation basis. Then we should ask which one has the optimal sensing performance. Okay. Okay, so the third part, the third block, is a Nyquist pulse shaping. So Nyquist pulse shaping filter. So as we can see, after this modulation, we have a time domain discrete sequence X, and we should attach each of these Xn with a pulse. So the pulse is look like this. Okay, and then we got this continuous signal. So this is pulse shaping. And as you can see, if we're going to transmit this continuous time signal, we need to guarantee that the symbols, so the samples, so X, for example, X1, X2, X2, and X3, they have no mutual interference with each other. So that means, so you can see this is the first symbol, this is the second symbol, and if we sample at the top or at the maximum of these symbols, we need to sample exactly the same xn. But if there's a non-zero value here, as you can see, due to the tail of the adjacent symbols, then there will be interference, right? So we need to guarantee that there's zero inter-symbol interference. So that means we need to use Nyquist pulse. And this is a time domain Nyquist criterion, which means that if we consider the autocorrelation function of the pulse, so this is the autocorrelation function, which is denoted as p tau, then if you sample this p tau at the integer multiple of the symbol duration, we need that the non-zero sampling points should be exactly zero, and it is only non-zero when n equals to zero. Okay, so this is the classical zero ISI criterion in the time domain, which is also known as the Nyquist criterion. And it has an equivalent frequency domain next criterion, which is a translation of this condition into the frequency domain, which means folded spectrum. So folded spectrum means that if we perform the Fourier transform for the ACF, we got the power spectrum, right? We got the power spectrum. So this is a power spectrum of the pulse, and we need that this frequency domain. We need these pulses if we put the power spectrum in the frequency domain, and we do this frequency shifting, and then they add it together. They need to adds up to a constant. Okay, so this is a folded spectrum criteria to be satisfied if we're going to have zero ISI. Then we have the third question, which is that how does the pulse shaping determine the sensing performance? Okay, so I think before this work, there's no relevant papers consider how pulse shaping affect the sensing performance in a communication system. Okay, so that is the introduction for the communication system. And now we need to try to evaluate the sensing performance. So we need to consider the sensing performance metric. So here, in particular, we look at the ranging task, which means that we're doing distance range estimation for multiple targets. And in such a case, we need to use autocorrelation function as a performance metric, which has a definition like this. So we use this x tilde t to estimate the ranges of multiple targets. Then its ACF is defined like this. Okay. So ACF is a very fundamental metric for sensing. If we look at the mean lobe of the ACF, it represents a range resolution and is inversely proportional to the bandwidth. And if we look at the side lobe of the ACF, it represents the multi-target interference and corresponds to the signal processing methods of matched filtering. Okay, so this is the this is an example of ranging task for 3 targets. We have 3 targets, 1 strong target, and 1 very weak target, and 1 in between. So by performing matched filtering to the received echo waves, we will end up with this 3 peaks in the range domain, and each of these peaks is actually corresponding to a time shifted ACF and also scaled and time shifted ACF, and you can see that if the ACF has a very high side lobe, then the weak targets, its mean lobe, will be masked by the side lobe of a strong target, right? So in that case, we're unable to identify these weak targets. So in many radar works, people are focusing on how to reduce the side lobe level of the ACF such that we can improve the ranging performance. Okay, so so as you can see, this is the range profile generated by the matched filtering operation, which is the linear combination of many of multiple time shifted ACF, right? So this is ACF shifted by the delay of some certain targets, and then combined together, which finally generates this so-called range profile or the matched filtering output. Okay, so this is a sensing performance metric autocorrelation function, which is also known as the zero Doppler cut of the ambiguity function. Now, the second aspect for sensing is that we can typically do coherent integration. So what is coherent integration? So if the targets remain stationary or quasi-stationary across, let's see, m transmission loads, one may improve the sensing performance by randomly realizing m symbol sequences, which are IID, from certain constellation, and averaging over their corresponding matched filtering outputs like this. So imagine that we transmitted this M, symbol sequences to do sensing, and for each of the symbol sequence, we do matched filtering. We get this YSM tau. Then we add them together and divided by M. We can actually reduce the noise, and also in particular in the random signaling case, we can reduce the saddle level generated by the random signals. So this is a coherent integration operation, okay? And in this case, you can see that combined to the standard matched filtering, here we have a coherently integrated ACF. So that means that we generate M, IID symbol sequences leading to MID ACFs, and then we average them, over to get the sample average of this ACF. Then we get this coherently integrated ACF, which is R bar tau. Okay. Okay. So with that, this is a guide that we wish to analyze for sensing, performance. Now, note that we are considering the random signaling, right? So we cannot just look at a single realization of this R bar tau. Instead, we need to consider its statistical properties. Okay, and in particular, we look at the expectation of the squared ACF. So here, expectation rather than a single realization to reflect the average performance of the random ISAC signals. And here the square is imposed because this R tau is a complex function, and we need to evaluate its saddle level. So we impose a square over ACF, and then we take the expectation, and this expectation is with respect to the random symbols, right? With respect to this S here. Okay, so this is the very fundamental and key performance metric that we are going to analyze throughout this talk. So before we could analyze this guy, we need first of all to have a discrete version of this R bar tau, because this continuous integration is a little bit complicated to process. So we simply do oversampling to for the ISAC signal at a ratio of L. Okay, so here TS is the sampling duration, and T is a symbol duration. So L means the number of samples within a symbol. So if L is equal to 1, then we get exactly Nyquist sampling. Then we get exactly this discrete time domain sequence X. But if L is larger than 1, this is oversampling, right? And with oversampling, we could, as you can see, represent, first of all, the X tilde T into this form. So remember that X tilde T is a convolution between X and PT, right? So here we could first compute the convolution of X and delta T, and then we convolve with the pulse itself, PT. So this is a basic knowledge from signals and systems. And this convolution is periodical convolution here because we consider signals with CP, okay? And then we sample this X tilde T in this formulation. That means we just replace this T by KTS, and K is an integer, TS is the sampling interval, okay? Then we get this. And so this is still looks very dirty, right? We need to have a compact formulation for this equation. So fortunately, we could represent this equation with just a very clean matrix vector multiplication formulation. So here X tilde equals to PR X up, and X up is like this. We have X0, X1, Xn minus 1, and between each of these two samples, we have L minus 1 zeros, okay? L minus 1 zeros. So this is to mimic here the convolution between x and the delta function. Okay, so it's like this. So we have x up, and here the periodic convolution with the pulse can be represented as a matrix multiplication with a circulant matrix like this. Okay, so circulant matrix P. So here P0 from P0 to Pln-1 is the sampling points over the pulses. Okay, we have this Pk equals to Pkts. Then we can formulate this circulant matrix P and then multiply to x up, we get this x tilde. Okay, so this is a compact formulation of pulse-shaped ISAC signals like this. And with that, we could represent this, discrete squared periodic ACF in this formulation. We get this x tilde, which is here, and again, and to consider the convolution or autocorrelation function of x tilde, we use this JK matrix. So this is a periodic time shift matrix. As you can see, we have so you can see this is composed by two identity matrices and two zero matrices. Here the one identity matrix is of size k, the other is with size Ln minus k. So imagine that you multiply this JK with x tilde. You're doing nothing but we move the the k samples at the tails of x to the head of x, right? So it's simply a periodic time shift of x, which is to represent to generate the effect of time delay for the signal. So we get this discrete squared PACF. Now, if we're going to derive this expectation, we also need to represent this ACF in the frequency domain, which could be much easier to deal with. So the frequency domain representation is like this. So here, J tilde NK is the folded spectrum, just like I mentioned before. And this G is the power spectrum of the pulse. And here, this V matrix is the Fourier transform of U, okay? Fourier transform of U. And then we just put each of its column here to multiply to S. And then outside here is, this is the, IDFT, okay? So this is a frequency domain representation of this RK inside this expectation. So now we're going to compute the expectation of the squared ACF. So very fortunately and very elegantly, we could derive the closed form of this expectation under arbitrary modulation basis, arbitrary constellation mapping, and arbitrary Nyquist pulse shaping. Okay, so basically this is a very generic equation for any valid communication signals. So we could also divide this expectation of the squared ACF into two parts. So this part is the square of the expectation of this RK. Note that this is different from this guy, right? So this is the expectation of the square, and this is the square of the expectation. Okay, and we call this part an iceberg. So it is the the IDFT of the power spectrum of the pulse, and it is nothing but the autocorrelation function of the Nyquist pulse itself, and we'll call it iceberg. And I'll show you reason why in the next slide. And this part, which is a variance of the RK, RK, we call it sea level. Okay, so it is contributed by, as you can see, the constellation kurtosis here, this kappa, and the modulation basis, which is embedded in this V tilde. So V tilde is like this. It is element-wise square of this V matrix. Okay, it is also known as a best stochastic matrix, and each of its rows and columns sums to 1. So this is the modulation basis or the waveform. And here G tilde K is the power spectrum of the pulse. Okay, so basically this part is mainly due to the randomness of the signal, and this part is mainly due to the deterministic part of the signal. So I'll show you some examples here. Okay, so this is an example of let's see, OFDM's modulation with 16 QAM and RRC, so root raster cosine pulse shaping. So as you can see, if we look at this blue line, this is the exactly this expectation of the autocorrelation square. Okay, so this blue line, which is like this, and this black line, this black dashed line, it represents the squared autocorrelation function of the pulse, which we call it an iceberg. Okay, and we call this part, which represents the variance, we call this part a sea level. So why is that? Because you can see that if we do coherent integration, so if we do m times coherent integration, we can reduce the variance, and which exposes more of the iceberg part, more of the deterministic part of the ACF. Okay, so as you can see, we could very vividly describe this part as this variance as the sea level, and this dashed lines as the iceberg. And if you do coherent integration, you can reduce the sea level and expose more of the tips of the iceberg, right? So this is the so-called iceberg sea level metaphor for this ACF characterization. Okay, so as you can see here, we're doing 100 coherent integration, and by doing so, we can reduce the setup level by 20 dB, right? So just as predicted by our equation here. So this is the iceberg and the sea level metaphor for the ACF of random ISAC signal. Now with that, we need to design each of these individual blocks of the communication systems such that we can control the this ACF on an average, right? We're trying to reduce the setup level of the of this ACF on the average, basically to reduce the expectation of the squared ACF. And what our design parameters are, first of all, the modulation basis U here, right? And here we have to also design the pulse, the power spectrum of the pulse shaping filter. And we also need to design the constellation. So here we, in particular, employ the probabilistic constellation shaping, which means that we control the transmission probabilities of each constellation point. So this is the input distribution of the constellation PS. And we wish to minimize the expectation of the squared ACF over some region that we're interested in. For example, this KSL region. So that means some setup level region that we're interested in. We try to reduce this part of the setup level, and we try to do this kind of minimization. So from the first glance, if we do not have this closed form expression, this can be very, very challenging, right? Because this is basically a stochastic optimization problem and has very complicated coupling effect on each of these, design parameters. But with this closed form, closed form expectation, we can see that actually these three parts, they are decoupled with each other. So why we see that? Because if we look at the modulation basis design, you can see that it only affects this part, right? So if we can minimize this part, we can reduce the sea level. And for the constellation design, it only affect the ACF through its kurtosis. So if we can reduce the kurtosis, we can also reduce the sea level. And finally, the power spectrum of the pulse-shaping filter, it mainly affects the iceberg part, because for this part, if we have a sufficiently large M, then the system performance will be mainly determined by the iceberg part, right? So basically, we could design each of these three parameters in a decoupled manner, which is a very good thing. And someone may ask about the mean lob, okay? So the mean lob here, if we have a given, let's see, a given neck-support shaping, given modulation basis, the average mean lob level is almost constant. It only depends on the kurtosis of a constellation. But as you can see, if M is sufficiently large, then this part can also be negligible. Then the average mean lob level is basically on a scale of n squared. Okay. So in such a case, we could only reduce the saddle lob level because the average mean lob level is basically a constant, and the mean lob width is inversely proportional to the bandwidth. It's like this, and also we have a roll-off factor of the pulse shaping filter. Okay, so this alpha is a roll-off factor. Okay, so this is the generic formulation for the communication-centric ISAC signal design, and we can now look at each of these parameters one by one and see how to design them by our optimization techniques. So the first one is the optimal modulation basis for ranging, and we consider two cases. One is stop-Gaussian case, which means that when this kappa is less than 2. So this is the relevant to most of the cases, because the QUAM and PSK, they all have constellation symbols that has a kurtosis less than 2, right? Okay, so if kurtosis is less than 2, then this is a negative, and we need to, if we minimize this part, we actually maximize this L2 norm, and with respect to this U matrix. So which can be written like this. Okay, so in our recent TIT paper here, we managed to prove that the maximizer for this problem is nothing but OFDM. Okay, it has this U matrix has this kind of structure. We have an IDFT matrix here, and we have a set n permutation matrix. So any set n permutation matrix is okay. And theta is so diagonal theta is a diagonal matrix with unit modulus entries. Okay, so all these kind of structures corresponds to OFDM modulation, subject to permutation and phase shifts in the subcarriers. Okay, so in such a case, we could prove that for all the sub-Gaussian constellations like QUAM and PSK, OFDM achieves the lowest average saddle lob level at every K, at every leg. Okay, so this is a very important discovery in this system, that we could manage to prove that OFDM achieves the optimal ranging performance on the random ISAC signaling. And the proof sketch is like this. So recall that this V tilde matrix, which has this kind of structure, is a bistochastic matrix. We could prove that the objective function is maximized when V tilde is any real permutation matrix pi. And this can be established by using the sure convexity of L2 norm and the concept of majorization theory. Okay, so in such a case, if V tilde is a permutation matrix, then this U matrix could be like this. Okay, so that is how we prove that OFDM is optimal. So when we got this result, it's also very surprising, and which looks very beautiful to us, because before our work, there are many arguments that OTFS or OFDM or AFDM could be a better sensing waveform for compared to OFDM. But here we managed to prove that OFDM is still optimal for sensing, in particular for ranging on the IID QUAM and PSK constellations. And this is, I think, a very remarkable result. Okay, and in the super Gaussian case, so we rarely use super Gaussian constellations, but for completeness, we also proved that for super Gaussian case, single carrier is optimal for ranging. Okay, single carrier achieves the lowest ranging saddle level at every saddle. So which is the duality for the OFDM. So this is again not OTFS nor the AFDM. So either OFDM or single carrier could be optimal for ranging. Okay, so this is the super Gaussian case, and these are the results for the optimal modulation basis. And if you look at these numerical results, we can see that so this is a 16 QAM and with raw factor of 0.35 RC pulse, n equals to 128, L equals to 10. So this is oversampling ratio. And you can see if we compare 5 modulation bases, single carrier, AFDM, OTFS, CDMA, and OFDM, we can see that OFDM always achieves the lowest average set-off level among these 5 modulation bases. Okay, so OFDM is, directly we can prove that it's optimal, and by simulation, it is also optimal in terms of ranging. And also, if we look at the coherent integration case, we can see that by, for example, 100 times integration, we get 20 dB integration gain in terms of the saddle level reduction. And again, the OFDM compared to single carrier in this case will consistently deliver the 5 dB gain compared to single carrier under 16 QAM. Okay, so this is the ACF examples for different modulation schemes. And now here we have a physical interpretation of the optimality for OFDM. So when we got these results, they are all mathematically correct. But some people asked us, so what is the physical interpretation behind these mathematical results? Okay, so finally we came up with this interpretation, and I think it's also very simple and very beautiful. So it is basically due to the Fourier duality and the central limit theorem. Okay, so now let's consider the very ideal case that we have a completely flat spectrum, frequency spectrum like this, right? So in such a case, we know that the ACF could be a delta function. So that is the Fourier duality, right, between the completely flat spectrum and the delta function. And the delta function is no wonder the perfect sensing autocorrelation function, right? Because it has no saddle lobes, 0 saddle lobes. But we know this is not possible, because if we have random symbols carried by this waveform, we get this fluctuation in the frequency domain like this, right? And then we get a saddle lobe levels, because the frequency domain is no longer ideally flat. So we get saddle lobe levels like this. Now we could conclude that to reduce these saddle lobe levels, we should reduce the frequency domain fluctuation in the amplitudes of the signal, right? So they are equivalent in the Fourier duality sense. Now, if we look at a so-called waveform or a so-called modulation, that is actually we put these IED symbols in some particular signaling domain, like in the frequency domain, like in the time domain, delay Doppler domain, or a fine frequency division domain. Okay, so or code domain. So in those cases, we will end up with these different waveforms, right? So no matter what domain you're using, if you put these symbols on some domain, its time domain representation is x equals to us, and u is this modulation waveforms. And its frequency domain representation is FNUS, right? FN is the DFT matrix. Okay, so in such a case, if we look at the frequency domain representation, we can see this is a unitary transform over S, because Fn is a unitary matrix and U is also a unitary matrix, and their multiplication also gives you a unitary matrix, right? So FNU is a unitary transform over S. So from the central limit theorem, we know that any unitary transform over this IID simple sequence make it approaching Gaussian, right? So this is the conclusion of central limit theorem. And we know that Gaussian constellation has a kurtosis of 2. So if you have sub-Gaussian constellation like QUAM, and if you perform a unitary transform over this, QUAM sequences, we will, inevitably increase its kurtosis because it's approach Gaussian, right? So in such a case, to reduce the, frequency domain fluctuation, which is actually proportional to the frequency domain kurtosis. So why it is proportional to the kurtosis of the frequency domain? Because the fluctuation of the frequency domain is the variance of the amplitudes, right? Amplitudes, spectrum, and it is also the variance of the squared amplitudes, right? So which constitutes to the fourth moment of this FNUS, which is a kurtosis in the frequency domain. So if we're going to reduce the fluctuation, we're just try to minimize the frequency domain kurtosis. And now we have FNUS, which is, every unitary transform will increase the kurtosis. Then the best thing that we can do is to keep this FNU as an identity matrix, which means that we do nothing about this S. So then its kurtosis will not change, right? It's still sub-Gaussian. So in that case, if FNU is an identity matrix, then U is IDFT, which corresponds to OFDM. Okay, so this is the optimality interpretation for the OFDM. Why OFDM achieves the lowest setup level? Because it achieves the lowest frequency domain kurtosis. Okay, so that is the physical interpretation. And then we look at the second block, which is the constellation. So in particular, we're trying to do probabilistic constellation shaping, PCS, to reduce this kappa, this kurtosis. Okay, so as you can see, if we can reduce this kurtosis to the minimum, we get the minimum sea level, the minimum settler level in the generated by random data. But we cannot reduce this kurtosis to as low as possible because it will definitely affect the communication performance, right? For example, if kurtosis is equal to 1, which is a minimum, it corresponds to PSK. But PSK has very poor communication performance, right? So we have to use QUAM. And then we formulate this, optimization problem in terms of the probabilities of S. Okay, so this is the input distribution of S, and this is a mutual information between the communication signal and this constellation S, and we also need this S, its fourth moment or the kurtosis to be less than some threshold. We use this to control the sea level part. And again, we need this regularity conditions of the constellations, like unit of variance and zero mean and zero pseudo variance. And this is actually a convex optimization problem over the probabilities. But since it's an optimization problem over probabilities, it is a functional optimization rather than a conventional optimization problem. And we could solve this problem use the so-called Blahoto-Arimoto algorithm, okay, like this. So we first equivalently formulated the mutual information in a very classical form that has been extensively used in information theory, and then we use Blahoto-Arimoto algorithm to iteratively optimize over this PS and the QS given YC, and then we get so we can do this kind of optimization until convergence. We then get this probability vector PS. Okay, so here is the results. So we look at the results for 16 QUAM and 64 QUAM. Okay, so these are the conventional QUAM constellations, and we use different color depth to represent the transmission probabilities. As you can see in standard QUAM constellations, each of these points is transmitted at a uniformly probability distribution. So for each of these points in 16 QAM, it will be transmitted at a probability of 1/16, right? And for this guy, it will be transmitted over a probability of 1/64. And by executing this optimization problem with a given kurtosis value, for example 1, then for this one we get a constant modulus cancellation, and for this one we get another sort of cancellation which is not a constant modulus but a nearly constant modulus cancellation. And if we can slightly increase this C0, this threshold, to 1.15 or 1.25, we get some cancellation points. All the cancellation points will be transmitted, but some may be transmitted at higher probabilities, and the other ones will be transmitted at lower probabilities, like this. And with this, we could achieve a trade-off between sensing and communication. So these two extreme points, this one is the PSK cancellation, and this one is a QAM cancellation. So this one has the optimal sensing performance, but poorest communication performance. And this one is the opposite. It has the optimal communication performance, but very poor sensing performance. And if we do time sharing between these two cancellations, we get this line segment with which is an inner bound. And if we can do this cancellation shaping, we get a better performance trade-off between sensing and communication, and in particular between PSK and QAM. Okay, so like this. So that is how we deal with the cancellation shaping by optimizing the kurtosis of the cancellation. And finally, we could look at the pulse shaping part. So now that we have this M, which is coherent integration times, if we have sufficiently large M, the sensing performance will depend mainly on the geometry of the iceberg, right? And then this iceberg is nothing but the IDFT of the power spectrum. So we can basically design the power spectrum itself. So we impose two objective functions. One is integrated set-lobe level. That means given a region of set-lobe that we're interested in, we add them all together to get this integrated set-lobe level. And on the other hand, we could also minimize the maximum set-lobe level over a given region. Okay, so this is a peak set-lobe level, which are two very typical cost functions in the radar literature. And also we need a roll-off constraint. So the roll-off part is a very important performance parameter in the pulse shaping. And with this roll-off constraints, you can see that all linear constraints in this power spectrum. So they're all linear. Okay, and here we also need this power spectrum to be monotically increasing or decreasing. And also we need to impose a power constraints here, and all these constraints, they are linear in the power spectrum. Okay, and so if we're doing optimization over this FISL and FPSL, we're actually optimizing a quadratic function over some linear constraints, which is convex. So I'm not going to introduce more details here. We just look at the results here. So we compare our results with the root arrested cosine pulse shaping. Okay. So for example, if we are interested in reduce the set-lobe level over a given delay region or the range region like this, right? Then we can consider the optimization of integrated set-lobe level or peak set-lobe level. We get this. So you can see by doing so, we could effectively reduce our set-lobe level here. And if we compare with the RRC, so this blue line there, the RRC, and with so after the 10,000 coherent integration, we can see with our designed pulse, we achieve like a nearly 20 dB reduction in the set-lobe level, which is very remarkable. And if we compare the power spectrum of the RRC pulse and the designed pulse, you can see they're nearly the same with just a slight modification over the RC, right, like this, okay? So it is very surprising to see that just a very slight modification over the power spectrum will generate a huge, reduction in the setup level. So this part we call iceberg shaping, which is to reduce the setup level of the iceberg part, the autocorrelation function of the pulse itself. Okay, so we can also compare the actual ranging performance for different pulses under different modulation and constellation. So this is the ranging performance for PSK with OFDM and the single carrier under designed pulse and RC. So as you can see, under single carrier, we can actually, identify nothing. So we consider a two-target ranging of, scenario that we have a strong target and we have a small target here. Okay, strong target is here and the small target is here. And in such a case, on the single carrier waveform, we can see that the mean lobe of the small target is completely masked by the set lobe of the strong target, right? So under both pulses, we can do nothing. We can identify nothing from this figure. So that is why we have a very high ranging MSE here. And if we change to OFDM, we get a much improved performance, as you can see. And under our designed pulse, we get an even better performance compared to the RC, because the RC has very high setup level here, and which can be identified as fake peak, which generates high ranging errors. Okay, so this is the ranging performance for PSK. And this is a ranging performance for QAM, and in particular for 16 QAM. And we consider, in this case, the coherent integration for the multiple pulses. And as you can see, with 1,000 coherent integration, we could improve our performance, our ranging performance, by more than, let's see, 81%. And with our designed pulse, we can improve another 87% compared to the RC pulse. Okay, so that is again because the RC pulse has very high set level here, and it can be identified as fake targets. So this is the ranging RMSE for the QAM. Okay, finally, I would like to conclude this talk with some take-home message. So we have looked at the communication-centric ISAC design, signaling design on the practical communication system, and in particular, we look at this constellation mapping, its modulation basis, and the Nyquist pulse shaping filter design. And we can see that for ISAC systems using orthogonal modulation on the QAM PSK constellations and matched filtering algorithms, OFDM is the optimal ranging waveform, and there's no need to design new waveforms. And then the set lobe generated by the random data may be significantly reduced by coherent integration. And the sensing performance of communication signals may be significantly improved by constellation and pulse shaping design. Here are some of the future possible directions. So first one is sensing with coded communication signals, because in our current system setting, we look at fully IID symbols. But if we have correlation among symbols, that means we can do coding, channel coding before we do channel constellation mapping. Then we may introduce another degree of freedom to shape our sensing performance. So we can look at the sensing with coded communication signals. And then the other direction is the fully statistical characterization of the ambiguity function, because now in this series of work, we just look at the autocorrelation function, which is a ranging performance, and the Doppler performance is still need to be further investigated. And furthermore, we can look at non-orthogonal and nonlinear modulation, right? So currently we look at the orthogonal modulation basis, linear modulation basis. And finally, we could look at bastatic and multi-static sensing with communication signals. And here are some references of this line of research. And if you are interested in this topic, you could look at a very recent tutorial written by me, which has already been accepted by JSAC. And if you're looking at the pulse shaping design, constellation shaping design, and also modulation basis, you can look at these two papers. Okay, so here are all the talk I wish to deliver in this lecture, and I'm open for questions. Thanks for listening.
Okay, many thanks for Professor Liu's nice talk. And I have collected some questions from our online audience. So the first question is then, why is AFDM more suitable in high-speed scenarios compared to OFDM?
So this is a good question, but I would so from our current research, I would see, at least from the sensing aspect, AFDM is not as superior as OFDM, even in high mobility scenarios. Okay, so we have already analyzed the ambiguity function. So this, as I just said, this is autocorrelation function analysis in this talk, but in our ongoing work, we have already analyzed the ambiguity function, the full ambiguity function for all these waveforms under IID symbols. And what I can tell you is that the OFDM is again optimal in both delay and Doppler side lobe levels. Okay, so I could see that OFDM is still optimal under, even you have high mobility, even you have Doppler effects. So perhaps in the communication side, AFDM is superior to OFDM in high mobility scenarios, but for sensing, I don't think so. Yeah.
Okay, thanks for your very clear explanations. And the second question is about the trade-off between sensing and communications. So the question is, could you provide a concrete example of how a specific design choice, such as the modulation order or pulse shaping filter, improves the sensing performance, but at the cost of communication performance, such as data rate or bit error rate?
This is a very good question. So, as I just said, in this talk we have looked at 3 blocks design, right? We have modulation, we have constellation, and we have pulse shaping. So for modulation basis, here we have proved that OFDM is optimal for sensing on the IID format and PSK. And fortunately, you can see that OFDM is also the by default modulation basis for 4G and 5G communication. So with this, you can see that sensing already achieves its optimality on the OFDM without the loss of optimality in communication, right? So this is a win-win situation that both communication and sensing, has a very good performance on the OFDM. So this is for the optimal modulation basis. And the other part is the constellation shaping here. So here, it definitely has a trade-off, just like I said. For sensing, PSK is optimal. But for communication, QAM will achieve better communication rate, right? So if we wish to improve our sensing performance, we have to sacrifice a little bit of the communication rate. For example, if we wish to improve our detection probability to, let's see, 0.9, here, as you can see, compared to the this 64 QAM, we could lose some communication rate, some spectral efficiency, like, for example, 0.4 bps per hertz. Okay, so with this design, but if you do time sharing, you will need to sacrifice more rates. So with this design, we actually improve our communication performance on the given sensing performance. So that is the constellation shaping. It will definitely has a performance trade-off between sensing and communication. And the third part is the Nyquist pulse shaping. And this part, again, it's like a modulation basis. It will, minimize or improve our sensing performance without the loss of the communication performance, because we impose the Nyquist property in the pulse shaping design, that means there will be zero inter-symbol interference, and then the communication rate will, keeps the same. And since we have the same roll-off factor, the same bandwidth, the spectral efficiency will also keep the same. And the only change is that we reduce the setup level of the sensing performance. And again, this is a win-win situation for both communication and the sensing. So I would see in this 3-block design, there will be only trade-off in the constellation shaping. And in modulation and the pulse shaping, there will be no trade-off. Both communication and sensing will have very good performance. Okay, I think that's my answer.
Okay, many thanks. And the next question, I think this issue is not covered in this talk, but I think maybe many people are interested in this question. It is about the standards of ISAC. So could you please share some information about the discussions in standardization organizations regarding the ISAC waveforms?
So from what I know, there's currently no discussion on ISAC waveform standardization, but there is some discussion on the 6G waveform for communication. So actually, I have already introduced in the first lecture that in the August, the 3GPP has reached an agreement that 6G will continually use OFDM as the default waveform in both downlink and uplink. Okay, so 6G will use OFDM again for communication. And given the optimality of OFDM in ranging, in sensing, we could believe that for ISAC, OFDM is also the standardized waveform in 6G. So I don't think that OTFS and AFDM will be standardized in this generation. Maybe in the future generations. Yeah.
Okay, many thanks for your viewpoint. And okay, so that's all for the questions. And because we have no further questions, so maybe we can stop here. And thanks again, Professor Liu, for your very nice talk. Thank you.
Okay, thank you very much.
Thank you. Bye.